Hello and welcome back to the continuing series of lectures on machine learning. We did cover the framework and setting up of the support vector machine as an optimization problem, and we'll continue from there. But before I do that, I just wanted to show you something that goes supplementary to the lectures that are being delivered. So this is a blog that me and my student we have built. Okay, at a very elementary level, the blog aims to introduce the fundamentals of machine learning, and the introduction and description of each and every aspect of machine learning or whatever we intended to cover is written in such a way that it's sort of an easy read. Okay, and therefore the lectures will actually complement the content of the blog, and this is under Creative Commons, and so therefore there is no problem in sharing the content with anyone. Okay, so this is my student Rahul Yadida, and he is going to be a full-time graduate student at North Carolina State University soon with full scholarship, and this is me. Right, and so you can see we start with introduction and prerequisites, and there are a bunch of things that we covered, including regression models and also some classification, the Gaussian discriminant analysis. Some of the content that's here is additional to what I have covered so far, and support vector machines up to regularization and some clustering methods. Okay, in fact most of the clustering methods, and there is some little short notes on some of the things such as k-nearest neighbor. Okay, however, what happens is, if I show you one sample, if I go to linear regression, it introduces linear regression with a very high level idea. Okay, and some of the very basics, like what is a training example, what is a test example, what is a hypothesis, right? Okay, and introduces things in a sort of an intuitive manner rather than it's a not a intensively mathematical treatment. However, my lectures are, right, and so therefore these two things hopefully will supplement each other. And more importantly, what we have done here is we have introduced some data sets, and most of these data sets, wherever we could, we actually attributed the credit to the original source. So in this case, this is Andrew Ng's Coursera, which is CS229, right? It's a pretty famous course, and the data is borrowed from there. It's a pretty popular housing price data, and Python snippets are explained here, and each and every aspect of the theory is also explained. Okay, some of the things, like for example, I haven't really talked about stochastic gradient descent or batch gradient descent, right? But those are basically methods, particularly batch gradient descent, where all the data is available to you at one shot. Okay, and so therefore each and every aspect of the theory has been explained through code. Okay, all right, and these codes are reproducible. We have tested all these code quite well. Okay, all right, and so therefore similarly, like if I click on regularization, you can see therefore simple examples are given. Okay, that's about it. Okay, so I just wanted to show you this blog. One other thing, that the notes that were developed in preparation for the course will also be added. Those things are not added here because we didn't have the time to type it up. So what I'm going to do is I'm going to upload the PDFs wherever those files are relevant. Okay, by strictly following the indexing pattern in the website. Okay, and we will also add some things like neural networks, basic neural networks with the backpropagation example and all that. Okay, having said that, let's move back to what we were doing, which is support vector machine. Okay, all right. So what we know is that we have a problem, right, where there are some training examples, right, and basically the training examples, instead of being separated by a single hyperplane, there are two support vectors that are designed, right, and there is a vector orthogonal in the direction of the decision boundary. And typically what we want to do is we want to have training examples separated as positive and negative training examples, right? So this is, if you recall, this is typically what we wanted to have, right? Okay, so this is a negative training example, and then this one is a positive training example, u plus, and then you complete the triangle, and basically you want to find out this length. This is pretty easy to find out, right? But the thing is, what we wanted to do, if you recall, we wanted to have this vector project in the direction of the orthogonal vector, right? So basically what you have to do is you have to multiply this by the unit vector, I mean, which is nothing but the w divided by its norm. Okay, if you do that, you actually end up with an optimization problem, because this is the width that you want to maximize. This is the width we want to maximize. Okay, all right. So how do we do that? I mean, we introduced, if you recall, we introduced a variable to characterize training examples. Okay, and also to set up constraints corresponding to the width in such a way that, you know, we don't want any of the training examples to fall here. Okay, all right. So therefore, I mean, you figure out that condition, which is nothing but, you know, the characteristic variable was yi, right? And then, you know, yi plus corresponding to +1 for positive training examples, and yi minus corresponding to -1 for negative training examples. And then take the inner product of yi with the, you know, yi with the wi x plus b. Okay, all right. Okay, so after, you know, so basically the constraint was that you have the training examples xi, okay, plus b, right, -1 equal to 0. Okay, so that's it, that's the constraint. Okay, the other constraint was that since you are using the unit vector, the, you know, the length of the unit vector is 1. Okay, all right. Having said that, we went ahead to formulate the optimization problem. Okay, all right. And what was the optimization problem? The optimization problem was actually maximize the width, correct? So it is max 2 by w, right? Okay, which, you know, sort of can be written as mean 1/2 w square. So sort of a dual. Okay, all right, subject to the constraints that yi and norm of w being 1. So this is the optimization problem that we set up. Okay, all right. So having said that, I mean, what we wanted to sort of figure out whether this is a feasible optimization problem. Okay, all right, whether this is this feasible problem to solve computationally. Okay, why do we ask the question? It's like this. I mean, well, I mean, we have this constraint over here, right? I mean, what does this represent? This represents some geometry, right? I mean, so it's sort of like, if I look at this, I mean, it's sort of represents a sphere, okay, with radius 1. Okay, the question is this a hollow sphere or a solid sphere? Now, if I pick 2 points, okay, I mean, so what this represents is basically represents the circumference, right? Everything, all the points on the circumference, because they are at a distance 1 from the center, right? So these are a bunch of points. So let's say I have some x1 here and some x2 here. Okay, all right. Now, since these 2 points lie on the surface and satisfy the equations, I have sort of, you know, x1 equal to 1, right, and x2 also equal to 1. Okay. Also, since it's norm, what I can also say is that I could also have negative x1 equal to 1. Okay, All right. Now, the problem is, I mean, if I take a combination of these two, I mean, if I add these two, right, I mean, x1 and negative x1, then I should get a line segment, right? Where does that line segment lie? Actually, if you add, you can easily see that you have to pass through 0. But the problem is, I mean, typically what happens is, I mean, let's say this is x1, this is negative x1, right? Okay. You have to pass through the center, 0. Okay. Something like that. So any 2 points on the circumference of this sphere, if you want to add, right, which is nothing but a convex combination of these 2 points, correct? Okay. It will have to go through the inside of the sphere. But the way this sphere is, it's a shallow sphere, it's hollow. So there is nothing inside. On the contrary, if I have norm of W less than equal to 1, I can actually have any 2 points on the circumference and I add that, and that will, the line segment joining these 2 points will also go through the inside of the sphere, and we are okay, right? So, I mean, so this is actually a non-convex surface. Okay, so what's the implication of a non-convex surface? A non-convex surface. So if you have a so the constraint, I mean, typically what we want is we want a convex optimization problem, because a convex optimization problem guarantees solutions to converge and it's computationally tractable. It's solvable in a polynomial time. But if it's a non-convex problem, there is no guarantee that the solution could be achieved in polynomial time. So a non-convex problem, in fact, the objective function was also non-convex, but we transformed the non-convex objective function to a convex objective function. However, the constraint itself is non-convex. So typically what we do is instead, so we have to, because I had like, think of this as 1 over norm of W, right? Maximize 1 over norm of W. This is equivalent to writing minimize just the norm of W. So you take the inverse of it. Okay. All right. Now, so we have one norm. So where is this? But here what we see is we see a square. So where does that square come from? Well, that square comes from here. So what we do here is we remove this from here and you push the constraint up in the objective function itself. Okay. So therefore, and this 1/2 is just for an adjustment, criteria, so that when you take the derivative of it, this cancels out with the 2. So we rewrite the optimization problem so that it becomes convex. Okay. And how do we do that? So this is minimize 1/2 norm of W square subject to the constraints yi xi W plus b minus 1 equal to 0. Okay. This is convex because I removed the non-convex constraint. Okay. All right. So this is fine. This is fine. So this is like, this is sort of like since this is a quadratic expression, right? So this becomes a sort of a quadratic program. Okay. All right. It's a quadratic program. Admits of a positive, basically quadratic form. So it's like, the Hessian could be positive semi-definite, right? And therefore you could be able to, find the solution to all that. Okay. Now what we see here is this is like an optimization problem. If I did not have this condition, this would be an unconstrained optimization problem. Okay. Easy to solve. But I have the optimization of the objective function controlled by this condition. Okay. So what we have to do is what is known as a Lagrangian. Okay. Which is nothing but you write a combination of the objective function and, multiply the constraint by some scalar and, pose it as one function instead of two different ones. Okay. So we introduce the Lagrangian in the following fashion. Basically copy everything. So what you have seen here is that, this is the constraint, right? This is the constraint that is brought into, written together with the objective function and then, multiplied with a bunch of scalars. Okay. All right. So what happens is, I mean, by doing this, you have converted this to a single function that you want to optimize. Now, we need to first figure out here which ones are constants and which ones are not. Okay. Well, I mean, these are training examples, right? I mean, these are examples. So this is data. We know that, right? Yi is defined, right? I mean, it's defined as either +1 or -1 based on whether your training examples are positive or negative, right? The alpha i's are also, these are scalars, right? Okay, so what are the variables here? So the variables are W and B. Please recall, this is exactly what we wanted to, what we said previously, right? I mean, that we wanted to compute these, okay? So therefore, when you do the optimization, you do two things. You compute the partial derivative with respect to W, and you compute the partial derivative with respect to B. Okay, all right, that is exactly what we are going to do. Okay, all right, so let's do that. So when you do this delta L delta W, okay, the first term is easy because 1/2 and then it becomes just a W, right? Minus alpha I yi xi, because you are differentiating with respect to W, and set this equal to 0. That's one of the first condition of the Lagrangian. If you do that, I have W equal to alpha I yi xi. Okay, how do I interpret this? I mean, your alphas are all scalars, right? I mean, this, and summation is from overall training examples I equal to 1 to n, right? Yi is a characteristic variable, right? And it can either take a +1 value or a -1 value, and xi are the all examples, all training examples. So what you are writing here on the right hand side is a combination of all training examples. Okay, all right. So I mean, instead of all sorts of nasty things, I mean, you can actually write your weight vector as a linear combination of all training examples. Okay, great. So this is one condition that we have. The next condition is when you take the partial derivative with respect to B. When you do that, it's easy enough to see the first term will vanish, right? When you do this, so you have an alpha I B, right? And so alpha I yi, right? So you have just an alpha I yi with a minus sign, right? And that's about it. Set that equal to 0 as well. I mean, if you do that, what you can see here is that your alpha I yi's are nothing but 0. Okay, right? So solving so you have simultaneous equations, right? I mean, what we are trying to do, we are trying to solve for W and we're trying to solve for B, right? So therefore, I mean, by simply using this, I can rewrite the Lagrangian in the following fashion. It's 1/2, right? And I know that W is this, and norm of W square is nothing but the inner product of W with itself. Okay, so this is nothing but an inner product of W with itself. Okay, all right. Now what we know is that the summation of alpha I yi is 0 and W is nothing but this. So what we can do is you write W as this here, okay, and then again repeat that. But the only thing that you should consider is the indices will change, right? Because if the indices won't change, you would actually be taking the inner product of the same training example with itself. So that's exactly what we do. So we write W, which is nothing but summation alpha I yi xi, comma, right, summation alpha j yj xj. Okay, makes sense, right? And then we expand the other expression. I mean, if you do that, you have like alpha I yi xi, and then you have a W, right? And this W you once again write it as summation alpha j yj xj. Okay, and then you have a term which is summation alpha I yi b, right? Okay, all right, and summation alpha I. Okay, all right. Now, I mean, if you really look at this, what you see here is that, you know, the first two, I mean, this guy, right? I mean, let me choose a different color. I mean, this guy and this guy are really the same. They're the same inner product, right? Okay, and therefore, I mean, I can simplify this further by you know, combining this is 1/2 and this is the whole of it, right? So I can just combine these two, right? Okay, so let's do that. So if I combine these two, I will get a negative 1/2, you know. Okay, all right, this is what I get, and then these terms are sort of you know, gotten. Okay, and what we also know is that the summation of alpha I yi, right? You can b, because b does not have an index, right? So you can pull b out of the summation sign, and summation alpha I yi is 0. We see that here from here, right? So plug that condition, so this term will vanish. Okay, so this term will vanish, and so therefore I simplify all this, and what I obtain? I obtain the Lagrangian to be equal to sum of all the scalars that I have, okay, and these are the scalars that I could, you know, solve, minus 1/2. I just take these summations out, one sum on I, one sum on j, so alpha I, alpha j, yi, yj, and just the inner product of xi, xj. Because look here, in inner products we have this property, right? I mean, if you have scalars inside the inner products, you can actually pull the scalars out, right? I mean, so summation alpha I yi and summation alpha j yj are scalars. So pull those out and you just are left with the training example. So what you see here is that, you know, this is actually nothing but a dual formulation of the primal problem. Okay, so this was the primal problem. This is the primal problem. And this is the dual formulation. Okay, I mean, what is a primal and dual? It's very simple. I mean, for example, you take a matrix, right? Take its transpose, right? Okay, so you can write the matrix, any matrix, as a matter of fact, as any matrix A as its transpose of transpose. So the idea is the dual of the dual becomes the primal problem. So if you think of the matrix A as primal, and then the, you know, the dual problem is the A transpose, right? Okay. In other words, what you do is, you know, if it's a maximization problem, you just convert it to a minimization problem, right? Okay, and then you do the minimization of that again, you are back to the original problem. So that's the whole idea. Okay, all right. So in other words, basically what we also see is that the L function depends only on the training examples, only on xi and xj, which are the training examples. As a matter of fact, it just depends on the inner product of these training examples. So what it really means is, we know that when you take the inner product of, you know, vectors, it's an inner product, is a cheap operation. The computational complexity is of the order of n, right? I mean, when you take the inner product, right, the computational complexity is of the order of n. It's cheap operation. So what seemed to be an extremely difficult optimization problem just boils down to computing the inner products. Okay, all right. So assuming that the classes are linearly separable, okay, we are able to write the SVM classification problem, the two-class classification problem, as an optimization problem, in other words, and it simply boils down to computing just the inner products. Okay, all right. So remember, we had a decision rule, right? I mean, we had a decision rule. I mean, if you recall, that there's a decision rule was that you wanted something like this, right? Okay, and that thing simply boils down to taking inner products. Okay, so this was the original problem. This is what we wanted to do, right? Okay, you wanted to have some separating hyperplanes, 2 separating hyperplanes to be precise. Okay, so that your training examples, these examples are, classified as positive as well as negative. And these actually boil down to, computing a bunch of scalars through a Lagrangian and computing the inner products of the training examples itself. Okay, so in a nutshell, this is support vector machine for you. Okay, this is the SVM framework. Okay, all right. Thank you. So when we come back, we would actually talk about some of the nuances of support vector machines. Namely, how do we do regularization? How do we control outliers, right? What do we do when the classes are not linearly separable? Okay, and all of these tricks. Okay. All right. Let me go back to the blog and show you basically the same formulation, the primal problem. It's written in a similar manner, right? Okay. And if I go back, I would also mention the Karush-Kuntekar condition, which I did not mention here explicitly. Okay, and this particular subsection shows you how to implement a linear 2-class SVM from the scikit-learn. Okay, all right. And basically, what you see here is a GG plot, right? Which clearly states that I do have, I could really have 2 separating hyperplanes, and if I draw 2 separating hyperplanes, there are the classes which are linearly separated. Okay, all right. And then each and the maximization operation and everything has been written, and you note the correspondence. And this is the Python snippet that you implement, and you see that the classes are really linearly separated. This is basically, these are the around the red lines you see 2 separating supporting hyperplanes. Okay, all right. And there is also somebody else's page which shows how to write an SVM without using a convex optimization library. Okay, and it relies on a sequential optimization problem called SMO. But however, I'm not going to talk about that. Okay, more when we come back.